So first of all, I would like to thank the organizer of this very nice program and Dorte for the invitation to the conference. So today I will talk about our journey around this unitary limit, looking to bosons, and I will use a lot of information you get by the previous talker. So I will start with the description of universal window. You heard a lot today. You heard a lot about zero range. I will give my interpretation of finite range universality. And then I try to understand how this finite range can work, or it does work on the case of helium-4. I want to construct kind of a potential description based on mostly inspired by effective field theory. And I will try to understand how it construct it and if it works. So what we learned today that at low energy, the two-body physics is governed by the two-body scattering length. And we have usually we have two regimes. We have a regime in which the scattering length is more or less the same size as the interaction length, and so we have a weak interacting system, which works for two-body, but which also works for an infinite number of bodies. So you can use the same scattering length to describe a Bosonian condensate, and moreover, you can use a Bosonian condensate to measure the scattering length. But there is this regime where the scattering length is much greater than the interaction length, and we enter a non-perturbative regime. The two-body sector, still the two-body scattering length govern the physics, but we have, for instance, a bound state which is non-perturbative. But as far as we change the number of particles, the scattering length is not more enough, and we need another parameter. So we have, for instance, the Efimov effect, what we heard today, and we have this new free body parameter which emerge. And as Bira told us today, we need another free body force in order to describe the system at the same order as the scattering length. And we just heard about helium-4. Helium-4 is the most natural candidate inside this universal window. And this is more or less a reproduction of what has been shown before. I just go quick because we have a lot. So the first evidence of these shallow states were in the 90s in the group of Tönnies. And as we just heard in the group of Dörner with the head of Dörte, they also measured the first excited state of helium-4. So in the end, the zero range in description, what I told just now, it's like writing the effective range expansion, just considering the first term of this expansion, so just the scattering length. But we know that there are other terms. There is the effective range, and there are shape parameters. So what happens is that if we look at this regime where the scattering length is much bigger than the typical interaction length, these shape parameters, which in principle could be of order 1, happens to be very small. This has been known for the time of nuclear physics. They already noticed this. And this is true also for helium-4. That means, so in first approximation, we can truncate this effective range expansion to this order. So I have 2 parameters now. This gives, in some way, the simplest S matrix. So the simplest possible S matrix has 2 poles. There is one pole which is just the bounce or virtual two-body state. So AB is another way to write the two-body energy. I can call it binding length. And there is another pole. And this pole has been known for 100 years now. And it is a spurious pole. It's not a pole which corresponds to a real state. It is there just to fulfill all the mathematical good behavior of S matrix. And the location is given by the inverse of this RB. RB, it happens to be just the difference between the scattering length and this binding length. And it is a constant. In this schema, if we stay up to the second order, if you neglect shape parameters, it's just a constant. And there is a relation, an exact relation between the effective range, the scattering length, and this AB and RAB. This is another way to write, if you want, the effective range expansion. There exists a potential, the Eckert potential, which is the local potential, which has this S matrix. So it has exactly this S matrix. So this potential has no shape parameters. We can use this potential to relate AB and A. So the binding energy, if you want, as a function of the scattering length, scaled by the effective range. So this is the relation you have. You have only this relation. And it's, I repeat, it's valid if, it's exactly valid if the shape parameters are 0. And I can try to put data on this plane. So here is helium. I took the data from a DIRT seminar of 2 weeks ago, and taken from this potential CVP, MJS, which, as far as I understand, is one of the best potential to which describe helium. And if you take the data calculated with this potential, which one can think of like experimental data, it goes on top of this curve. You can use another potential. Usually I use this M2 potential as Bira showed also today, just like experimental data for a theoretical playground. And also it is on top of this curve. There is a small difference between helium described by this potential, and if you change the potential, you just move around this point. You can take also deuteron. You can take the data from deuteron, and still you are on top of this curve. You can play the game to take the potential, in this case I have LM2M2, and to change its strength. This lambda is a just number to multiply the potential, and you move around always along this curve. So this is correspond to lambda equal 1, but you see you could in principle tune this potential to reproduce also this datum. You can move all around, also up to deuteron if you want. You can use whatever potential, simple potential two-body potential you want. I usually use Gaussian because it's much simpler to deal with. And still, you have you move the strength of the Gaussian. You move all this on top of this curve, and you can reproduce or see this data. So just to summarize, this is my point of view of finite range universality. In this, if you are close to the unitary limit, the shape parameters are more or less 0 for, not 0, are very, very small. But in first approximation, we can consider B as a constant. It works for what I showed you before, but it works also for the other observables. So if you look at asymptotic constant, you have the form which depends only on AB or B for all the potential you want, all the physics you want, close in this window. You can do the same. You can play the same game for the mean square radius. It's the same. And as you see, you can recover the zero range limit just putting RB equal 0. In that case, A equal AB. And this is 1, 1, and these are just the prediction of a zero range theory. But this kind of universal scaling function is nothing else than the inverse of the probability of the particle to be outside the interaction region. So I use the potential, the Gaussian potential to describe this kind of physics, and we'll try to improve smoothly my description, taking these Gaussian potentials or constructing this Gaussian potential inspired by the effective field theory. As data, as done by previously Abira, I take the N2 N2 potential just because there are precise calculation up to 7 particles which I need, and I use the potentials, the Gaussian potential is kind of linear order. And when I say linear order, because I have in my idea, I have a small parameter, which is the ratio between the effective range and the scattering length for this particular atom, which is 7%. So in my idea is that I want to describe the systems up to with errors of the order of 7%. But what I want, when I say I want to describe the systems, I don't want to only describe the two-body system. I want to describe the n-body system in this with this precision. So these are so one can make a calculation, one can fix the scattering length, one can reproduce one datum, and we see that AB is always reproduced inside this leading order band of 7%. And if you, like Bira told us, you take the limit of R0 0, you have a zero range of theory, so it's consistent. But we see that in this region, there is a possibility to also reproduce the effective range to the same accuracy. And there is a special point, maybe just an accident, where you can reproduce the scattering length, the binding length, and the effective range with only one Gaussian. I call it a kind of a triple point. So, as I told you, I want this work also for an n-body system. And as soon as I go to the higher order, so I calculate 3, 4, 5 body, what happens is that I cannot describe this system inside this 7% band. And as you see, as R0 goes to 0, you have the Thomas collapse. And as Vera told us today, you need a free-body force in order to stabilize the system. But as I don't want to move R0, what I do is that I fix R0, so the equivalent of cutoff, and look at the system as a number of particles. And I ask for the stability as a number of particles grow. And if I do nothing, I have the collapse, even if I fix R0. And so this is a complementary way to see the necessity of a free body force at this order. So we put a free body force, we have 2 parameters, and we have a family of parameters which fix the free body energy. So we want to fix a datum, we fix the free body energy. And clearly, this family gives us different values in the free body sector. But if I look at the four body sector, one means I just reproduce the experimental datum. There is the possibility to reproduce the experimental datum up to this kind of triple point. And so I can choose, I choose to use this freedom just to fit the four body up to here. Then it's not more possible. And this is the result. The result is that, so this, the four bodies has been fixed. So I choose this family just to fix this. And I calculate what happens up to 7 particles. And what I see is that they kind of concentrate on this triple point. So the accident which was happening in the two bodies, also happening in the at least 7 body. But we had also previous calculation. It's a little different potential, but we had a similar calculation up to the continuum. And what you see is that once you fix the four body force, all the other states are reproduced at the same level of accuracy, even the saturation energy. Now I try to extend this game. I go to the next leading order. I just focus on the two body. If I focus on the two body, now I have the possibility to fix true data. Before it was just A, now I can fix also the effective range. And I look at how it varies with the range of the two body force. And I put this, I just draw the evolution of the states. And I put this free state because are the free extreme state, in the sense that this is the left and the right one also at the two body level reproduce the free body energy. And the center one corresponds to the case of V1 equals 0, which is just the previous leading order triple point. Because now we are reproducing A, RB, R, E, and also RB. And these free potentials correspond to these free lines. So the dashed lines, vertical line are just the extreme case where I also reproduce the free body force. In fact, if you look at the free body, here I have 1 and 1. And in the middle, I have the leading order. So clearly, even in this case, I see that my system is not stable. And I know that already I have a free body leading force already from the previous step. So I use this free body force. And with the free body force, I can somehow have a better description of the system. But as I told you before, I would like naively to have all the system described inside this epsilon square band, which now is 5/1000. And there are these points which seems to be inside. The triple point is not. But what poses puzzle is the fact that, or a problem, more than a puzzle, it's a problem, is that this extreme point, they were the points where the free body force already reproduced the free body energy. So in this case, I don't have the free body force. Or if you want, the strength of the free body force is 0. And we come back to what I saw before. The system is unstable. So at this order, I need, at this order, I need another force. So as Bira skipped, it went very fast, but it has been already proposed in the perturbative scheme that you need a four-body force. And as far as I understand, they propose a four-body force because the free-body force can be reabsorbed on the leading order free-body force, something like this. But I can have a free-body force, so I want to analyze what I can do with a next to the leading free-body force. So I give me this possibility, and now I have a few parameters still to play, and I tried to see if with this parameter I can describe my system up to this next to the leading order simple-minded description. And the fact is that in principle, I can. So I can find parameters in order to describe at least at 7 particles, to describe the system inside this 5 per 1,000 precision. It's not clear if I can, that means it's very sensitive, this fitting procedure. So it's not clear if I can really extend on all or not. But it seems that it's promising, to say the least. It's clear that another kind of force, or variable force, can do the job. So in principle, I could have used the four-body force. It's not excluding the four-body force at this order. And in fact, always naively, I would expect that if I have a new free-body force, I can fix on a free-body atom. So the free-body atom which we thought about is the atom dimer scattering length. So we look at the atom scattering length, and we try to see if we could fix this atom dimer scattering length and describe at the same time the energies. These are the results. So if we just calculate the atom dimer scattering length at NLO in the two-body sector, but without at all free-body force, so this is the result. So we are quite far from the small band. I remember, I recall you that is 5 per 1,000 band. Then if we use just the free-body, we add to the next leading order the free-body force, which comes from the leading order, we get better results, but still we are far. And as we expect, we can fit this new observable inside the band. The problem is that the forces are kind of little different. And as I told you, it was very sensitive, the fitting was very sensitive. It happens that it doesn't seem possible to have a good result for both the atom dimer scattering length and the many body energies. So maybe this is one place where one can see that maybe there is also a four-body force, and the two are present at the same time. So, conclusion. Too fast. Oh, okay, not one. So, what I tried to do in this kind of game is to construct a simple mind potential for a system which is inside the unitary window. We decided to to take helium-4, it's clear that for helium-4 it's kind of useless because we know a very precise ab initio potential. But this is important for instance, in nuclear physics where the potential is not very known. So to play this game in a very controlled playground, it's quite easier. This potential has been kind of inspired by effective field theory. My simple point of view is that if you have a small parameter, you should, like a kind of Taylor expansion, you should have your description of the observable order by order better in a controlled way. As you want, as I use potential, and as people also in nuclear physics, finally they use potentials. It's interesting. It has been interesting to see the role of the potential ranges, which are in effective field theory language are the cutoff. So as people keep it finite, it's nice to see how the physics depends on them and what we can learn about. As I want to change the potential, I lose the possibility to see if there were different forces, what was the hierarchy or the forces by sending this cutoff to infinity or the range to 0. So I use as a criterion the fact that I want the system to be stable and to be described at the same level of accuracy as I take n to infinity. At least if there is no phase transition, I don't see why it should be 2 should be different from 4, 5, 6. And with this, I will end with just the list of the collaborators. So Paolo Recchia is my PhD. Alejandro is here. Michele maybe will come tomorrow. Luca is the expert of our expert in effective field theory. And Natasha, Arthur, and Bruno, they took care of the calculation in the n-body system. Unfortunately, Arturo passed away 2 years ago. So with this, I will just finish. Okay.
Yes, Eric.
In what you told us, it was very crucial. There was a positive scattering length in order to get a bound state. What would you do with negative scattering length?
You can do the same. That means the crucial point is to have a shallow state. So even it could be a bound or virtual state.
Okay.
So I didn't show that means the previous picture I show of this Eckart universal line. You can put also the nucleon virtual state. And they are there, always on top of this curve.
Thanks. Would you just go back and flash the Eckart potential? I just haven't seen it before. I just want to look at it again. But thanks.
This potential. I learned about this potential in some old notes on the 60s because when people were doing field theory, they, in order to have some results from some non-perturbative results, they summed all the bubble only, and they got this simplest metrics, and then they claimed that there was this potential. So this is, I looked at the paper of Eckart is in the 30s. Then there is Bartman who in the 40s had this nice paper where it does kind of inverse scattering. So he decides the form of the S matrix and construct all the families of the potential which has this kind of S matrix. And extra potential is one of these. So this is the simple local potential. So I think that you can do also with no local potential. This is this is the simplest local potential.
So I wanted to ask, because you mentioned, right, for helium case, it's possible to calculate from quantum chemistry this many body terms, in contrast maybe to other cases, right? So somehow, is there any way to compare like your effective potential, like effective many body terms to this like ab initio terms? I don't know. Somehow. I
don't think so. They are in nature a little different. That means, as Bira told us today, that means maybe whatever system you want to describe it as a hierarchy of forces. Then you can play in the sense that you can put some information which comes from a free body force in the two body potential. So what I think is that this, because I think that with this scheme you cannot really reproduce the real in the sense the ab initio free body, a two body potential. And in the same sense, you will always need a free body force, which is not the same free body force as you could calculate from ab initio.
Yes, so this I agree, but maybe somehow you could use the information, because like the scheme from quantum chemistry is like, it's well defined. Yes. Maybe you could use this as a kind of guidance for somehow the best way of doing, because I fully understand that there is like mixture of that free body term is mixed with two body and then just effectively you get, but somehow because here like the unknown questions, like what kind of really form and what parameters you have to use. So maybe, I don't know, this could be kind of example or
I don't know,
maybe some partiality, some parameters or not. You think it's not really not the, because it's so far away, so it does not make sense.
Yeah, I think yes, because from my point of view, we are kind of describing just low energy. So we are, in some way, we are just introducing the free body information which are inside the low energy data. So maybe there are other observables which are higher energy, which in some way goes outside this window, which are not described, cannot be described by this schema. And so, but it will probably well be described by the ab initio free body force. So I'm not claiming this is the theory of helium-4 in the exact. This is one sector of helium-4, which are energy of the energy of the states of the n-body state. But it's clear that there are other observables which are more sensitive to the short-range interaction, which are not described with this scheme.
Mario, the three-body force you inserted in your system, it looks to have two pieces, but one probably is repulsive. I don't know if the other one is attractive.
Usually,
yes, this the next one you have. Yes, the two pieces. This is to make your trimer more shallow.
This is I use this to fix as always the trimer. So the trimer is fixed. Then the extra freedom I used to try to put my spectrum inside this small band. So I changed the parameters. So you can imagine that you have three parameters: the two strength and the range of the free body force. And you can try to move this, so you fix the free body. In principle, I would like to fit also another free body parameter, because it's like when you go to next leading order, and this is what we try to do with atom dimer. But it seems that you cannot describe at once a new free body atom and the energies. So you have to, this is why I was, this is repulsive. Okay. And this can be, this is attractive. This is what we found. That means, so this which works at a shorter range, it's
Primacy before.
Mario, I believe it should work with stabilization with number of particles only if your last many-body force is repulsive. Because if you imagine that it's attractive, in the end, because number of combinations with many particles will grow faster than smaller number combinations, it will collapse.
Right. This is why I've been working here at this level. I've been working only between these two values of R naught, because in this region, my free body energies is bigger. So I need a repulsive force. I didn't go here and here because in this case, I have an attractive free body force which will surely make the system collapse. So this is what I use also.
Other question, Neil? You have.
NLO terms are perturbative or not perturbative?
Always non-perturbative.
Thanks.
So, Mario, maybe I can follow up with a question. You're aiming for something like 0.5% accuracy, if I understood you correctly for this. What's the accuracy of the calculations that you're using as a reference? I do much better than this. It means I can be. That means I show the numbers. Here, more or less, you are at the same accuracy. So I can reproduce these numbers exactly. That means when I look at, that means here I take as this number exact. So I compare with this. So this is 1/3000. This is an experimental data. You see. In this sense, I use this as good numbers. So I imagine that Nira, he knows better than me because he was part of this calculation, I imagine. So, well, because I don't have, these are Monte Carlo calculations as far as I understand, and the JAMA calculation are more precise than what I need.
More questions?
Vera wants the last word.
No, we have more time.
You have time? We have time? Okay. Well, Harold is listening and he says, I always want to have the last word. So let me ask that question. So as you know, Mario, I find this tremendously interesting. So I think it's worth contrasting it with what we do with effect field theory. And then I have a question at the end. But yeah. First of all, when you have that curve for the accurate potential, looks very much like a straight line to me.
But it's not.
In a first approximation.
Yeah.
And that's just to emphasize, that's what we do, right? We start with a straight line and we consider the deviation from the straight line in perturbation theory. When we do this, we do in a systematic expansion, and then we go to the three-body system, and there's a lot of work there, particularly by Dan Phillips, who is here only in spirit, but okay. So when you look at the three-body system at NLO, you see that there is no need for renormalization need for a three-body force. So you check at n square LO, and at n square LO, there's not only a need for a new three-body force, but also, from my understanding, is that at that point, the effects are consistent with being n square LO. So it's not, for us, it's not arbitrary to say that this three-body force is n LO or n square LO. It comes up, all the arguments suggest it's n square LO. And therefore, at NLO, when you go to the four-body system, we're stuck with this four-body force. It's not that we want it there, it's what's needed. So it's not really a choice. I mean, you can always promote three-body force or whatever, but then if you do that, you might have trouble. And maybe that's what's happening to you, I don't know. So finally, the question. So if I forget about your, what you call NLO three-body force, can you handle a four-body force? Or can you do calculations with a four-body force? Or you don't want to do them? Or are you planning to do that? Or what's the prospect for that?
It's for me, it's easier to do four-body calculation to have a four-body force than this next to leading order three-body force. So no, but it's not. It was. I want to make the point. It's not that I want to be in contrast with this effective theory. But what I want to be is to try to understand, in the sense that in the end, what happens is that people, even if they agree, and I totally agree, even if my knowledge of effective theory is very, very small, I totally agree on the theory and how things in principle should have been done. But the practice is that people use potentials in nuclear physics. They use potential with finite ranges. And they use, in the practice, as far as I understand, they use this freedom to fit data also. So I want to explore this because I'm able, that means there are other groups which do the perturbative thing. I am able to do non-perturbative. And I want to see what is the role of this cutoff. Because it seems in the two-body sector, okay, it's kind of accident. But when you have things like this, and which propagates up to the liquid, the accident seems to hide something else. So maybe there is another degree of freedom. We talk, I think, about this. Maybe there is a kind of dibarion, which plays a role. And but I think we need some exploration, and this was the aim of this work. Is just to see how things depends on the range, because people in the end they use it. Then so I can use the four-body force, and the last two. This is the fact that this fitting and this fitting, they are not really in agreement, maybe suggest that I have to add. But this doesn't mean that, as far as I understand, this is Luca, the effective theory guy. As far as I understand, maybe that it seems that he told me that if you work at finite range, you can have this free body next to leading force. That means, as I understand, it is in your scheme, it is absorbed in the leading order Freebody force. So if you take the zero range limit or the infinite cutoff, maybe I'm wrong, but then they can discuss. But it's not that there is no space for the Freebody force. It's that I would like, in my simple mind, I would like to add a simple force which adjust the system smoothly. So I wanted this to fix also the atom diameter. It doesn't.
Gandolfi first. So yes, we already. Let us give a space.
Okay, thank you for the nice talk. I have probably a very naive question. So what happens if in this expression you use two different cutoffs or two different row zero for the first and second term, and then use just the leading order three-body force?
There is a lot of space, I agree. There are some studies on using in nuclear physics, some recent study on multiple cutoff theory. So,
yeah, but if the ultimate goal for pionless CFT, for example, is to send the cutoff to infinity, it doesn't matter if I use two values, but I have an extra free parameter to play with. And then maybe I don't need the extra term in the three-body force.
But this is the schema that they are proposing. But then, yes, this, if I understand well, you put yourself inside the perturbative schema, or not? That means I don't, as far as I understand, you cannot. That means I have a kind of guiding line. I want to describe the data up to epsilon square. And it doesn't happen on what you say.
Well, my question is, do you need more terms or do you need more parameters?
I don't know.
Let us
maybe with different cutoff you can achieve the same. In some way, the naively way to see this is that I'm using the cutoff as a low energy constant. But
last
I don't want
question from Tobias. Just an observation. If we put now a four-body force, certainly the saturation properties of your liquid will be changed from only three-body forces, because I mean, maybe this can be seen if you begin to start to view these droplets in compare with a realistic calculation.
The practical point is that, for instance, here I can imagine to put a four-body force, you see, and which is repulsive, as was observed before. I need, if I had another force, it should be repulsive. The problem is that I'm not able at the moment to calculate the continuum. It was in the group of Arturo, who unfortunately died.
Okay, so thank you again, Mario.